Earth's elliptical dance, the 2025 precision update. Most people picture Earth traveling around the sun in a perfect circle, like a marble rolling around the rim of a bowl. This mental image feels comfortable and predictable, but it represents a fundamental misunderstanding of our planet's actual path through space. Earth's orbit forms an ellipse, not a circle, which means our distance from the sun changes dramatically throughout the year. This seemingly simple detail creates consequences that ripple through every aspect of life on our planet. NASA and ESA missions, including spacecraft tracking systems and the Gaia Observatory, have refined our measurements of these orbital variations to within just a few kilometers. These calculations reveal that our planet follows an elliptical path where the sun occupies one focal point, not the center. At our closest approach, called perihelion, Earth sits approximately 147.1 million kilometers from the sun. At our most distant point, known as aphelion, we drift out to roughly 152.1 million kilometers away. The difference between Earth's closest and farthest positions from the sun spans over 5 million kilometers. To put this distance in perspective, you could fit more than 390 Earth-sized planets in the gap between our perihelion and aphelion positions. This variation of 3.4% in our solar distance translates into significant changes in the amount of solar energy reaching our planet throughout the year. The timing of these orbital extremes creates effects that scientists continue to investigate. Earth reaches perihelion around January 3rd each year during the Northern Hemisphere's winter. Conversely, we reach aphelion around July 4th, in the middle of the Northern Hemisphere's summer. This timing means that Earth actually receives about 6.8% more solar radiation in January compared to July. The Southern Hemisphere experiences the opposite pattern, receiving its maximum solar input during its summer months when Earth sits closest to the sun. Advanced climate monitoring satellites can now detect subtle changes in atmospheric temperature, ocean currents, and ice sheet behavior that correlate with our changing distance from the sun. These measurements reveal that the elliptical orbit affects global weather patterns in ways that were impossible to detect with ground-based instruments alone. The gravitational dance between Earth and other planets adds another layer of complexity to our orbital motion. Jupiter and Saturn, the solar system's giant planets, exert gravitational forces that slowly modify Earth's elliptical path over time. These planetary influences cause what astronomers call perturbations, which gradually change the shape and orientation of our orbit across thousands of years. When Jupiter and Saturn align in their respective orbits, their combined gravitational pull creates measurable effects. Throughout the entire solar system, current research shows that Earth's orbital eccentricity fluctuates in predictable cycles spanning approximately 100,000 years. Right now, our orbit is slowly becoming more circular, approaching its least elliptical configuration in this long-term cycle. However, this gradual change occurs so slowly that human civilization has never experienced the more extreme orbital variations that occurred in Earth's distant past. During periods of maximum orbital eccentricity, the difference between perihelion and aphelion distances becomes much more pronounced. At these times, Earth receives up to 23% more solar radiation at its closest approach compared to its farthest point from the sun. These dramatic variations in solar input have contributed to major climate shifts throughout Earth's geological history, including the advance and retreat of massive ice sheets during glacial periods. The elliptical orbit also affects Earth's orbital velocity in accordance with Kepler's laws of planetary motion. When our planet approaches perihelion, it moves faster in its orbit to conserve angular momentum. During aphelion, Earth travels more slowly. This changing orbital speed means that the time Earth spins in different portions of its elliptical path varies throughout the year. The Northern Hemisphere's winter occurs during the faster portion of Earth's orbit, making northern winters slightly shorter than northern summers. Modern computer models incorporate these orbital variations with remarkable precision. Climate scientists use current orbital data to understand how past changes in Earth's elliptical path contributed to ice age cycles and other long-term climate patterns. These models also help predict how future orbital changes might influence global climate. although such changes occur over timescales far longer than human history. The gravitational influences from other planets create additional orbital complexities that recent research has begun to quantify with new accuracy. Mars, Venus, and the Moon all exert small but measurable gravitational effects on Earth's orbit. Even distant Uranus and Neptune contribute tiny perturbations that accumulate over millions of years. These combined influences mean that Earth's orbital parameters undergo constant, subtle modifications that affect our planet's long-term climate evolution. The precision of current orbital measurements has also improved our ability to predict future astronomical events. Scientists can now calculate the exact timing of perihelion and aphelion passages decades into the future, enabling more accurate climate modeling and agricultural planning. This enhanced understanding of Earth's orbital mechanics provides crucial data for space mission planning, as spacecraft trajectories must account for our planet's changing position and velocity throughout its elliptical path. Yet this elliptical dance around the Sun represents only one component of Earth's true motion through space. While our planet traces its annual elliptical path, something even more surprising occurs within our solar system itself. The gravitational relationships that govern planetary motion create unexpected movements that challenge our basic assumptions about how celestial bodies behave. The solar system's hidden wobble. The Sun itself moves in response to these gravitational forces, creating a wobbling motion that affects our entire solar system's path through space. When you picture the solar system, you probably imagine planets orbiting around a perfectly stationary sun that sits motionless at the center like a cosmic lighthouse. This mental image appears in textbooks, planetarium shows, and educational videos everywhere. However, this representation misses a crucial detail that fundamentally changes how we understand planetary motion. The Sun doesn't remain fixed in space while planets dance around it. Instead, our star constantly moves in response to gravitational forces from the planets themselves, creating a complex wobbling motion that affects the entire solar system's journey through space. Jupiter, the largest planet in our solar system, possesses such enormous mass that it exerts a gravitational pull strong enough to move the Sun. This isn't a gentle nudge or minor influence. Jupiter's gravitational force actually causes the Sun to orbit around a point located outside the Sun's own surface. This gravitational interaction creates what astronomers call barycentric motion, where both the Sun and Jupiter orbit around their common center of mass, known as the barycenter. Vera and Gaia astrometry missions have provided precise measurements of this solar wobble using advanced space-based observations. Scientists can now track the Sun's position relative to distant background stars with extraordinary precision, showing that our star moves in a complex pattern influenced by multiple planets simultaneously. These measurements demonstrate that the Sun travels in an intricate path that combines influences from Jupiter, Saturn, and the other giant planets. The resulting motion creates a multi-layered wobble that changes the Sun's position by hundreds of thousands of kilometers over the course of several years. Saturn adds another significant gravitational influence to this cosmic dance. When Jupiter and Saturn align in their orbits, their combined gravitational effects create even more pronounced movements in the Sun's position. These planetary alignments occur regularly, creating predictable patterns in the Sun's wobbling motion. Jupiter and Saturn shift the Sun's position by about one solar radius, carrying planets in a shared wobble that fundamentally alters the gravitational center of our entire solar system. These observations reveal that the Sun's movement follows complex patterns that repeat over multiple decades. The wobbling motion shows clear correlations with the orbital periods of the giant planets, confirming that planetary gravitational forces drive these solar movements. This wobbling motion has profound implications for understanding our solar system's path through the galaxy. As the Sun moves in response to planetary gravitational forces, it carries all the planets along with it on this shifting trajectory. The entire solar system's helical path through space becomes influenced by these internal gravitational dynamics. Instead of following a smooth spiral through the galaxy, our solar system actually traces a more complex pattern that reflects the Sun's internal wobbling motion. The gravitational interactions extend beyond just the Sun and giant planets. Mars, Venus, Earth, and even the smaller rocky planets contribute their own gravitational influences to the system's overall dynamics. While these contributions are much smaller than those from Jupiter and Saturn, they add additional layers of complexity to the Sun's movement. These smaller gravitational effects accumulate over time, creating subtle but measurable changes in the solar system's trajectory through space. What appears as simple planetary orbits from our Earth-based perspective actually represents an intricate gravitational choreography involving every object in the solar system. Each planet influences every other planet, and all planets collectively influence the Sun's position and movement. This creates a dynamic system where gravitational forces constantly adjust and readjust the positions and velocities of all solar system objects. The apparently stable orbits we observe are actually the result of these complex gravitational interactions reaching a dynamic equilibrium. These gravitational dances become even more fascinating when we consider how they compound as the entire system moves through space at galactic speeds. The Sun's wobbling motion gets superimposed onto its high-speed journey around the galactic center. This means that the solar system's path through the galaxy includes not just a large-scale spiral motion, but also smaller-scale variations caused by internal gravitational dynamics. The resulting trajectory becomes a spiral within a spiral, creating an incredibly complex three-dimensional path through space. The internal motion within our solar system creates patterns that affect our galactic journey in unexpected ways. As the Sun wobbles in response to planetary gravitational forces, it changes the solar system's orientation relative to nearby stars and galactic structures. These orientation changes can influence how our solar system encounters cosmic dust, stellar winds, and radiation from other astronomical objects. The timing of these encounters depends partly on the internal gravitational dynamics that cause the Sun's wobbling motion. Recent studies have identified correlations between the Sun's barycentric motion and various astronomical phenomena. The wobbling motion affects the solar system's magnetic field structure and its interaction with the interstellar medium. As our system moves through different regions of space, the Sun's changing position influences how effectively the solar magnetic field deflects cosmic rays and other high-energy particles from reaching the inner planets. The revelation that Jupiter pulls the Sun so strongly that our star actually orbits a point outside its own surface fundamentally changes how we perceive our cosmic neighborhood. The Sun, which appears so dominant and central from our perspective, actually participates in a gravitational partnership with its planets. This partnership creates a dynamic system where the gravitational center constantly shifts based on planetary positions and alignments. Our entire solar system becomes a complex gravitational ballet where every participant influences the dance, contributing to the intricate helical pattern we trace through the galaxy. These internal dynamics create subtle variations in our orbital patterns that accumulate over vast timescales, potentially influencing Earth's long-term environmental cycles in ways scientists are only beginning to understand. Milankovitch cycles and the Ice Age connection. Among the most significant patterns emerging from this orbital complexity are the climate cycles first identified by Serbian mathematician Milutin Milankovitch. These cycles reveal how subtle changes in Earth's orbital parameters create profound effects on our planet's climate over thousands of years. Milankovitch identified three primary orbital variations that influence Earth's climate: changes in orbital eccentricity, axial tilt, and axial precession. Each operates on different timescales and creates complex interactions that drive long-term climate patterns. The eccentricity cycle determines how elliptical Earth's orbit becomes over approximately 100,000 years. When our orbit becomes more elongated, the variation in solar radiation between perihelion and aphelion increases dramatically. During periods of maximum orbital eccentricity, Earth receives up to 23% more solar radiation at its closest approach compared to its farthest point from the Sun. These extreme variations in solar input can amplify seasonal climate differences and contribute to transitions between glacial and interglacial periods. The obliquity cycle controls variations in Earth's axial tilt over roughly 41,000 years. Current measurements show that our planet's tilt ranges between 22.1 and 24.5 degrees, and this variation creates profound differences in how solar radiation reaches different parts of Earth's surface. Earth's tilt is gradually decreasing, moving toward the lower end of its range. This decreasing obliquity creates milder seasonal contrasts and promotes an overall cooling trend across the planet. The reduced tilt means that high-latitude regions receive less intense summer radiation, preventing complete melting of winter snow and ice accumulation. The precession cycle affects the timing of seasons relative to Earth's orbital position, completing its pattern over about 25,700 years. This wobbling motion of Earth's axis changes which hemisphere receives more intense solar radiation during different seasons. Currently, the northern hemisphere experiences winter during perihelion, when Earth sits closest to the Sun. However, precession gradually shifts this timing, creating cyclical changes in seasonal intensity that interact with the other orbital variations. These three cycles combine to create the complex climate patterns observed in Earth's geological record. The 100,000-year eccentricity cycle has become particularly prominent in recent Ice Age patterns, though scientists continue to debate why this cycle gained dominance over the shorter obliquity and precession cycles during the past million years. The transition to 100,000-year pacing in Ice Age cycles represents one of the most significant changes in Earth's climate system, and researchers are still working to understand the mechanisms that cause this shift. Advanced climate modeling now incorporates precise measurements of Earth's orbital parameters with unprecedented accuracy. Scientists can track changes in Earth's axial tilt with precision measured in arcseconds, revealing subtle variations that translate into significant climate effects over thousands of years. These measurements show that orbital influences on climate operate through complex feedback mechanisms involving ice sheets, ocean circulation, and atmospheric composition. Computational models can now predict future Ice Age cycles based on orbital mechanics with remarkable precision. These calculations show that the next natural Ice Age cycle should begin in approximately 50,000 years, assuming no other factors intervene. However, current atmospheric carbon dioxide levels may delay or prevent this natural cooling cycle. The enhanced greenhouse effect from human activities could override the orbital cooling influences that would normally trigger ice sheet expansion. The interaction between natural orbital cycles and human climate impact creates unprecedented complexity in climate prediction. While Milankovitch cycles have controlled Earth's long-term climate patterns for millions of years, the rapid increase in greenhouse gas concentrations over the past century introduces variables that didn't exist during previous orbital cycles. Climate scientists must now account for both natural orbital influences and anthropogenic factors when modeling future climate scenarios. Recent discoveries reveal that these orbital cycles themselves may be influenced by our solar system's movement through the galaxy. As our solar system travels through different galactic environments, it encounters varying gravitational influences from nearby stars and stellar clusters. These external gravitational forces can subtly modify Earth's orbital parameters over very long timescales, adding another layer of complexity to Milankovitch cycle predictions. Our galaxy's structure plays a crucial role in these orbital modifications. The plane of our solar system sits tilted at approximately 60 degrees relative to the galactic plane, creating a unique orientation that affects how external gravitational forces influence planetary orbits. As we move through different regions of the galaxy, the gravitational environment around our solar system changes in ways that can alter the timing and intensity of orbital cycles. Modern climate models now incorporate data about our galactic position and movement to improve long-term climate predictions. Scientists track our solar system's position relative to spiral arms, stellar associations, and other galactic features that could influence Earth's orbital dynamics and climate. This galactic perspective reveals that Earth's climate history reflects not just local orbital changes, but also our planet's journey through the dynamic galactic environment. These comprehensive models suggest that understanding Earth's true motion requires looking beyond simple orbital mechanics to consider our entire solar system's journey through space. The speeds and distances involved in this galactic voyage dwarf even the most extreme terrestrial velocities, creating a cosmic context that fundamentally changes how the Milky Way our planet's movement through the universe. 220 kilometers per second. The scale of this galactic journey becomes clear when we examine the actual numbers behind our solar system's motion.